So the name of this talk is Reducing LLM Calls with Vector Search Patterns. I have already gave you an idea of what we're going to be talking about. But before we actually get started, I'd like to talk about the Stack Overflow developer survey that came out like 2 or 3 weeks ago. I just wanted to mention that Redis has been selected as the agent data storage tool, the most popular one by the developer community. And this is interesting because if you've built real-time applications before, you've probably used Redis. So Redis has become kind of the foundational infrastructure for real-time applications. And what we're trying to position ourselves today is also as the foundational infrastructure for applied AI applications. Having said that, I'd like to talk about something else. That is, just because you can doesn't mean you should, all right? So GPT-5 was out a couple weeks ago as well. And every time a new model comes out, people say that it's the death of RAG. So you can see in this example, for example, this guy says GPT-5 is out, but it's not a good news to RAG. And the rationale behind it is because, as you can see here, GPT-5 has a context window of 256,000 tokens, which is not something out of this world because we had models with context windows of 1 million tokens before. But the difference with GPT-5 is that even when using all of these tokens, you can still expect the model to produce responses that are accurate and that uses all of the information that you send there. All right, so that's basically the rationale that people use this time to say that GPT-5 is the death of RAG. But the problem is, it's not because you can send 256,000 tokens with every prompt that you should do it, because it may become expensive very easily, right? So GPT-5 takes $1.25 for every million tokens that you that you input, basically. So it would mean that with every 4 requests, you would pay $1.25 to OpenAI, which is not ideal and it's not scalable as well. And this is one of the reasons why I wanted to make this talk as well, because I want to talk about vector search patterns to make agentic applications and also chatbots more efficiently, not only in terms of pricing of the money that we're spending, but also in terms of the time that it takes to process responses or do whatever it has to do. Today, we're going to talk about 3 different patterns. The first one is semantic classification. The second one is semantic routing. And finally, the last one is semantic caching. And we're going to go through 3 different challenges to exemplify how we can use these patterns in our applications. All right, so before we get started actually with the patterns, I'd just like to do a quick recap on vectors and vector search. As it was mentioned, I think the audience is kind of familiar with vectors and vector search. So I'm just going to do something very quick. So basically, when you're talking about text, text has encoded meaning, right? So it has discrete meaning that is not encoded by the characters or the ASCII numbers themselves, right? So one of the challenges computer scientists have had for quite a long time is actually how to encode the meaning behind text. Because if you get something like bad, that means that something is bad, is one definition for it. But if you think about, for example, not bad, it actually means the opposite, right? So how can you encode all the meaning of text? And a couple of years ago, 2013, a couple of researchers at Google DeepMind, if I'm not mistaken, they came up with Word2Vec, which was one of the first embedding models for actually encoding the meaning of words as numerical representations so that computers could work with these numerical representations faster, most efficiently as well. So basically, a vector is a representation, in this case, of a word as numbers that encodes the meaning of these words. And by having those, we can use vector search then to perform mathematical operations on them and understand how similar 2 pieces of text actually are. So you can look at 2 words, for example, and see how similar they are. We can look at 2 snippets of text or even larger text and try to understand if they're similar to each other, if they're synonyms. So if you look at the vector representation of the text, did the Apollo 11 crew go to the toilet? And the representation of the text, that is, did the astronauts of Apollo 11 went to the bathroom? When you look at those numbers, they should be somehow similar, and this could be seen mathematically so that a computer could understand that these 2 sentences are actually semantically related. So that's vectors and vector search in a very nutshell. I had prepared some slides for that, but since I understand that the audience is already familiar with that, I just wanted to get everybody on the same page. But I also have these videos so on YouTube. If you want to dive a little bit deeper later on, I invite you all to watch them as well. They're very short, like 3 to 6 minutes, depending on them. All right, so let's talk about the first challenge now, which is filtering posts or filtering text or classifying text. The example that I'm giving here is based on Blue Sky. So we have, like, if you guys are familiar with Blue Sky, it's a social network that is similar to Twitter. So you can post posts there that are up to 300 characters, small ones. And the challenge that I'm bringing here is giving a certain post, how can I classify that it actually belongs to some kind of label? So for example, I get some posts where they're talking about Redis and I want to make sure it's actually about Redis, right? How can I do that? There are different ways of doing that. I know at least 3 ways. One of them is by using an LLM. So you have here a social media post, for example, every repeated LLM call is money on fire. Redis 8 semantic caching understands meaning, not just keys. And what you can do is get the social media post and together with a prompt, send that to the LLM, asking it to return a response in a JSON format, for example, with a property inside of it saying that it's related to Redis with a true or false, and then using that response for whatever your application needs to do. The problem with this approach is that, as I mentioned before, when leveraging LLMs for that, you're going to be paying for the tokens that you're inputting and outputting for that, but also it might take a little while to compute the response for you. So let's say that you're classifying 1 million posts, for example, and each one is taking at least 1 second. You're going to take at least 1 million seconds, if you don't do that concurrently, to compute all of them, right? So this is one of the approaches, and I want to talk about another one that is by using a vector database. But before I actually talk about that one, there's one that is hidden here. I didn't put in the slides, but it's also interesting to talk about. That is by using zero-shot classification models. So those are AI models that are not LLMs. They're a little bit, they're smaller. Actually, they can run locally. They're more efficiently, and they're faster as well. So for example, I have a GIF here. So in this case, we're classifying the text. Java is a great programming language with a few possible labels, such as software programming or politics or something else. And then when you compute that using a zero-shot classification model, it's going to tell us what is the probability that this text actually is related to one of these labels. So that's zero-shot classification models, but this is still using AI. All right, and it may still take a few hundred milliseconds to compute. And that takes us to our third approach here, which is using a vector database. So the way you can classify text with a vector database is by getting a bunch of references. So in this case, I generated all of these references using an LLM, using ChatGPT, for example. I asked ChatGPT to generate 150 tweets about Redis, for example, and it came up with all of them. Here are 4 examples of those. So for example, pro tip, use scan instead of keys in production. Keys blocks the entire server while scan is not blocking, and so on. A lot of those references. And what I want to do with those references that are all related to Redis tweets that mention Redis or that are about Redis, I want to get them. I want to run them through an embedding model so I can turn them, each one of them, into vector representations. And then I want to store these vector representations inside of a vector database, which is Redis in this case. And after I've done that, whenever I get a new post, what I can do is I can run this post through an embedding model as well, the same one, and get the vector representation of this post and run a similarity search in the vector database, Redis in this case, to understand how similar this post is to all the references that I generated and stored inside of Redis. So hypothetically, this one could actually match the closest to this reference that was stored inside of Redis with a similarity score of 0.28. And the similarity score can go from 0 to 1, being 0 the most similar and 1 the most different. And given the threshold that I have defined, so let's say that I say that everything that is below 0.3 is similar enough, I could say, all right, this post is actually about Redis. So I don't have to call an LLM or a zero-shot classification model to classify this text. I can do that with a vector database and a couple hundred references that I have stored in there. And I'm just checking if the post is semantically similar to these references. And if it is, I know that I have classified that correctly, or yeah, correctly, basically. So I have a quick demo to show you as well. Where is it? So this demo is available for anybody who wants to try it. We have this repository, Redis AI resources, on GitHub. We have a lot of recipes for people that want to get started with AI using Redis. And the one that I want to focus on right now is this one, that is basic routing, so semantic routing. So semantic routing is the name of the technique that we're applying here for different use cases. I just saw that my Google Colab reset, so let's see if I'll have to run everything again, or if this is still running. So before I actually show the examples, I also want to talk about the Redis VL library, which is the Redis vector library, which is basically a library that is implemented by Redis in Python. It's also coming to Java and JavaScript to allow people to do semantic caching and semantic routing and vector search with Redis in a more abstract and easier way. And that's what we're going to be using for this example as well. So you can see that here I'm using the route object provided by the Redis VL, the Redis vector library. And here I'm defining a route. The name of this route is technology. And then I have some references here. So what are the latest advancements in AI? Tell me about the newest gadgets, what is trending in tech. And I have the same for sports and entertainment here. So I can classify texts with these routes based on technology, sports, or entertainment. And this is just for the sake of example. That's why we don't have a lot of references, just a couple of them. But what Redis VL is going to do under the hood is basically embed these references, each one of them separately, and then store them inside of Redis alongside the route that they refer to. After we have done that, oh, and there's one more thing. We're also defining the distance threshold here for each of these routes. All right, so let me see if this runs. Okay, I think it just reconnected and everything is still working. Let's find out. All right. And after I've done that, I can then try to classify some text based on this route. So I have here, for example, can you tell me about the latest in artificial intelligence? And if I run this one, it has classified that as technology. It has matched the route technology with the distance of 0.41, which is within the threshold. And it classified that correctly, even though I don't have artificial intelligence written in any of these references. I mean, I have the acronym here, but I don't have the actual words artificial intelligence or any of the words that we have here. I can also try to do something about sports. And I'm sorry for the British people that are watching, but I'm going to use the word soccer here. So can you list a few soccer players? So let's see if this works. Okay, so it matched sports with a distance of 0.68, which is within the threshold. But the reason why I wanted to use soccer here was to showcase that soccer is also not mentioned in any of the references here. We have football, we have sports, but they don't have soccer, and we were still able to match it correctly using semantic routing for classification here. And if I try to classify some text that is not related to any of the routes, as you can see here, are aliens real? It's not going to return any of them because it's not similar enough to any of the references that we have defined inside of our semantic route, basically. So that's semantic classification in a nutshell. Going back to the presentation right now. All right, so let's talk about challenge number 2, that is actually calling the right tools. All right, so when you're working with agentic applications or even chatbots, we can define tools that our LLM can interact with. And the way that it's usually done by most of the frameworks, such as Lancche or Spring AI, is by defining the tools inside of the prompt. All right, so you define the tools that are available for the LLM to work with, to define the parameters that it may receive, and so on. And then you're going to send this prompt to the LLM, and the LLM may return to you saying, hey, you should call this tool and give back to me the information that it returns. So if you're asking the LLM, for example, hey, what's the weather like? The LLM is stateless, it doesn't have this information, but you say that you have a weather API tool or a get weather function that it may call. It's going to return to your agentic application with the request to call this tool. You're going to call this tool. You're going to get the information that is retrieved from that, and then you're going to send the prompt again to the LLM with this information and all the rest that you had already sent, which means that you're basically computing the same prompt more than once. So you're paying for the same prompt more than once, and you're also taking double the time to process that. All right. And the different approach that we can take here is by using a vector database, by using semantic routes again, but in a slightly different way. So what we can do now is actually come up with some references that may relate to what people would actually ask your chatbot. So for example, what's the weather like? Or will it rain today? Or hello, what can you do? And then get these references to refer to a certain tool. So you can see that the first one is referring to get weather default city. That's the function. Or the what can you do is referring to greeting and help. That's the function it's referring to. And here we're going to do something similar to what we've done before. So we're going to get all of these references. We're going to run each one of them through an embedding model, get the vector that is the result from this embedding model, and store them in a vector database so we can run semantic search later on and see if the prompt of the user or from the agentic application is actually triggering any of these tools based on how similar it is to the references that we have stored in our database. Right, so this is the diagram that shows how it works. So basically, this is the user prompt. Hey, what are you capable of? And then we run that through an embedding model. We vectorize it. We get the vector, and we run a similarity search in our vector database. And then in this case, hypothetically, it has matched the reference, hello, what can you do? With a similarity score of 0.459, which is close enough. It's very similar. And then it means that our application should call the greeting and help function. And all of that without triggering the LLM. All right, so you can avoid triggering the LLM a lot of times by using semantic routing in this case as well. I don't really have a demo for tool calling, but I have another demo here that is for a route that allows you to block or set some guardrails in your chatbot that would work very similarly. All right, so have some blocked references here, for example, and these are, for example, things about extraterrestrials or corporate questions about Agile or anything about the S&P 500. So those are things that you don't want people to interact with their chatbot, and if they do, you don't want to trigger the LLM because you're going to be paying for tokens that are actually not related to your business, right? So you want to block those, or you want to call tools, as I showed you before. So you can come up with these references. You can come up with a route, as we did before. Let me run this one. And then whenever somebody comes with a question that is related to one of these references, such as what are the results of the Standard & Poor's, which is the S&P 500, you can see that it matched the block list with a distance of 0.44. Even though we don't mention Standard & Poor's here, it could still understand that this is related to the S&P 500. Or for example, I can also ask, is Scrum a great framework to work with? I don't mention Scrum in the references, but I talk about Agile. And since I talk about Agile, somehow my embedding model can understand that Scrum or this sentence is related to one of the sentences in the reference here. Or I could also ask a question such as, how many aliens have visited Earth? And in this case, it was also blocked because we have the reference things about extraterrestrials, and it's similar enough to this reference. Right? So this is semantic routing that can be used for tool calling or blocking references, setting guardrails for your chatbot or your agentic application, so you can avoid going to the LLM a lot of times, and you can avoid spending so much money and also wasting time computing so many responses. Right, so that was the second challenge. And now we have the third challenge, if there are no questions, that is caching the responses. All right, and I have already said that, but basically, or actually gave the examples, but I didn't say that. So let's say that you have a chatbot for your company, and you have a user that asks a question there, and then a couple of minutes later, they come back and ask the same question again. And every time you're sending the prompt to the LLM and computing the response and paying for that. and sometimes for things that you have already computed before that you could just reuse if you cache them. The problem with traditional caching here is that if you cache the actual string and they ask the same question but with different wording, you're not going to match the cached ones. So basically, the example that I gave, did the Apollo 11 crew, how did the Apollo 11 crew go to the toilet, for example? Or did the Apollo 11 astronauts go to the bathroom? Those are the same questions worded differently, right? So if you use an embedding model and a vector database, you can vectorize these prompts, store them in the vector database, and whenever something similar comes back, you can go to the vector database and retrieve the response from there instead of going to the LLM and computing the same response over and over again. So I have two diagrams here. The first one is showing the regular flow that is basically going to the LLM, asking the LLM to generate the response every time, and now they put in the message. And the second approach is by actually using a vector database and caching that prompt in the vector database. And every time you get a new one, you check if it has already been computed before, as I'm going to show in the demo right now. So this demo is not based on Redis VL. It's actually based on Spring AI. And this one has a more beautiful, or at least a little bit prettier user interface. So what I have here is I have stored inside of Redis, and I can show you that with Redis Insight, a lot of references about beers, basically. So you have the name of the beer and the alcohol of the beer and the description and so on. All of that is stored inside of Redis. So I'm using Redis as a knowledge base here. And we have the actual embedding here. So the vector representing the information that was stored for all of these documents, right? And what I want to do now is I want to ask questions about it. So for example, what kind of beer, maybe that's too small, let me zoom in. What kind of beer goes well with smoked meat, for example? So I can send that. And that's going to take a little while because since I'm asking that for the first time, it's triggering the LLM, and the LLM is going to take a little while to compute it. And I hope it works. It's taking a little longer than it should. Let's take a look at that. Okay, it worked. I think it was, we had some kind of cold start. Shouldn't have taken that long. Usually it would take like 2 seconds to compute that with the LLM. But you can see that the embedding time, so vectorizing the prompt is very quickly, took 10 milliseconds. The searching Redis was very quick as well through the knowledge base, took only 5 milliseconds. But the LLM is usually the bottleneck here because it takes at least 1-2 seconds to compute the response. But now if I ask the same question again with different wording, so what kind of beer goes well with, let's say, smoked beef? And I ask that, you see that the response came back much faster. It's the same response because it was cached inside of Redis using semantic caching. And that took only 25 milliseconds to run through the cache. So it was super fast. And you can also see the cached prompt here in Redis. So let me scan more because we have more than 20,000 here, semantic caching. So we have, for example, this is some tests that I did. Okay, so this is the one that we did right now. What kind of beer goes well with smoked meat? Here's the answer, and here's the vector that represents this text right here, all of these numbers right there.
Can you bump up the font size of the Redis interface a bit? It's really hard to read.
Yeah. Oh, sorry. Okay. Oop, that's too much. All right. Is it better now?
Yes.
Nice. So we have the answer, we have the embedding, so the vector with 384 dimensions, and we have the content that was vectorized here in the semantic caching, and you also have the knowledge base where we have all of the beers, 22,000 types of beers stored in Redis as part of the knowledge base. So this is semantic caching in a nutshell. This is also available for anybody that wants to try it out. We have another repository that is the Redis Spring Boot Resources repository with a lot of recipes there, feel related to AI. So if you want to try it out, feel free to do it. And now that we have talked about these 3 challenges, I want to talk about something else that is optimizing accuracy, because you can imagine that depending on the number of references that you have or the quality of references that you have inside of your database, the accuracy when you're trying to match them may not be good enough. And because of that, our applied AI engineering team has been researching ways of optimizing that. And one of the things they came up with is the Redis Retrieval Optimizer library. It's also for Python. And it has a couple of features here, but basically the idea of this optimizer is to take you from my search seems okay to I can prove this configuration is optimal. Because when you're doing vector search, it's kind of tricky to understand if the embedding model you're using is actually the best one you could be using, or if the results that are being retrieved are the most accurate ones. So this library is, the goal of this library is actually to help you with that. So you can see that the first feature here is to help you systematically test different embedding models and retrieval strategies. So basically, what embedding model should I be using for my vector search, for my RAG, for example? But the one that I want to focus on is the threshold optimization here that allows you to automatically tune the semantic cache and router thresholds. Because I showed you, and where was it? Right here, that when we're defining the routes, we can also define the distance threshold, right? And the way we did it here was mostly by ear, but by getting some test data and sending this data to the optimizer, it can run some optimizations there and come up with the best distance threshold for the routes that you have. So if you run that with this, it can come up with, okay, the best one for technology should be 0.3256, something like that. And then for the second one could be 0.45 and so on. It's going to do that work for you so that you don't have to worry about optimizing it yourself. But there are other strategies that you can apply as well. So if we're talking about semantic classification, for example, one of the things that you can do is self-improvement. So every time you classify a text correctly and you say, okay, this is about Redis, for example, which is what our classification was about, we can add this new post back to the vector database as a new reference to our semantic router. And within time, our semantic router is going to get better because you're going to get more references, and actually references that are not synthetically generated, but that came from real data. So within time, the accuracy is going to increase. But if the accuracy is still not good enough, another approach you can take is a hybrid approach, where basically if something is similar enough, we can say, okay, this is positive. We know that this is about Redis. We're going to move on with that. But if it's not similar enough and we say that it's a negative, we can assume that it may have been a false negative. And in this case, we fall back to the LLM and do the classification with the LLM and check the LLM if it's similar enough or not. Remembering that even the LLM is not going to be 100% accurate. Not even humans are going to be 100% accurate when doing classification, especially at scale. All right. And the best of both worlds here would be the semantic classification with the hybrid approach, but also with the self-improvement. So falling back to the LLM and also adding the posts as new references to the route so that it improves over time. And within time, we rely less and less on the LLM, saving costs and money along the way. So this is the self-improvement, the hybrid approach. So those are ways of improving the accuracy for semantic classification. But what about tool calling? All right, so tool calling, one thing that I tested, especially back in May during Kotlin Conf, was actually how could I improve the accuracy when the users may send prompts that give us a lot of information. Most of this information may not be related to the tool that they're trying to call. So in this case, for example, a user could be, let's say, talking to Alexa and saying, hey, I had a bad day yesterday. The weather was terrible and I crashed my bike onto a tree. Anyway, will it also rain today? And with all of this text, even if we vectorize it and then run a similarity search, it may not be related to anything that we have inside of our database as references because it's kind of random at the end of the day, right? So it can even match something completely different because when you're running similarity search or vector search, it is always going to return you some response or some vector back from the database. And in this case, you can see that similarity score was too high, meaning that it's very different and that it's actually called the wrong tool here, which is the greeting and help when it should have called the weather tool. So a way of improving the accuracy that I have researched already is by actually chunking this prompt into separate clauses. So by punctuation, for example. So we get and we chunk that into, hey, I had a bad day yesterday, the weather was terrible, and I crashed my bike onto a tree. All of those as separate texts. And then we vectorize each of them separately, and we run them in through the vector database separately. And eventually, and this is wrong, this should have called the weather tool here. One of them, for example, the last one, will it also rain today? There should have been two clauses as well anyway, and will it also rain today? Maybe very similar to will it rain today? That is one of the references, and then we can trigger the right tool more accurately by chunking the prompt into separate clauses as well. So this is a way of improving the accuracy of tool calling. But if you think about it, another caveat that we have here is that if we're using an LLM, we can actually extract parameters from the prompt as well. So all of the examples that I gave here are actually tools that don't require parameters, right? So what's the weather for the default city at today, for example? But there's been a lot of research. This is not the one, this is the one. Actually, there's been research on how to use vector databases to extract parameters from text as well. So this is one example that has been done by some people at PwC, but at Redis, we're also making researches to find out how we can improve the accuracy and even make tool calling more effective by using vector databases. Something that I'm looking forward to. And finally, we're talking about semantic caching as well. And one of the problems we can have with semantic caching is when we cache something that shouldn't be cached. Right, so let's say that you have a chat bot that is supposed to tell new jokes, just an example that I thought right now, and you ask it to tell a joke, and it caches the response, and then you ask it to tell a new joke, and then it uses the response that is cached instead of telling you a new joke. So that's something that may happen with your business model as well, depending on what people are asking. You should every time be computing a new response instead of getting one from the cache. And what you can do to mitigate this problem is by combining semantic caching with semantic router as well. So you can define some references that refer to some tools or prompts that shouldn't be cached. And if those are caught by the semantic route, for example, then it would call the LLM every time instead of relying on the semantic caching. Having said that, another problem that may happen with embedding models as well is that, for example, you can ask a chatbot, what's the capital of Paris? And then you cache the response. And then you may ask it, what's not the capital of Paris? And then it gets the cached response because they're similar enough, right? According to the embedding model. So to mitigate that problem as well, Redis has done some research on that. So this is the paper that we have put out back in April of this year, where we trained a specific embedding model, which we've called Lancche Embed v2 here. It's open source. It's available for anybody to use. You can just go to Hugging Face and use it yourself. But the idea of this model is to avoid this kind of examples that I just gave you about the capital of Paris, where they might be very similar, but actually mean something slightly different. And now the last thing that I wanted to talk about is Lancche itself, which is a managed semantic caching service provided by Redis. It's still in the experimental version, but if you don't want to go through the hassle of implementing a semantic caching yourself, you can just go to cloud.redis.io and spin up a semantic cache and use the API. You have libraries as well for JavaScript and Python, I think, so far, but more coming within time, that will allow you to cache the prompts of your users with Redis, with a service that is fully managed by ourselves. And that's basically everything that I had to share with you today. Again, my name is Rafael Delio. I've been working as a software engineer in the developer advocacy team inside of Redis. And I hope you have enjoyed the talk. Thank you very much.